To begin our discussion about phase behavior, we're going to start with a relatively simple system. So what I want you to think about is a system that's constant N, so total number of moles, constant total volume, and also a constant temperature. Okay? And so we have this constant NVT system that consists of a single pure component. And so by component, I mean just a molecular species. And so we just have a single pure molecular species, or i.e. chemical. So we have a single chemical, but it could form two different phases. And we're going to keep this general. So I'm not going to say liquid, solid, or vapor, but rather I'm going to say we have two phases of alpha and beta. Okay. All right. And so let's say in our constant NVT system, it looks like this, where in the bottom part of the system, we have the alpha phase, and in the top part of the system, we have the beta phase. Okay, so we'll call this beta up here, and we'll call this alpha down here. All right, and this N alpha refers to the number of molecules that are in the alpha phase. V alpha is the volume of the system that's in the alpha phase. And here, you'll notice that T is the same in both the alpha and beta phase, and that's because our entire system is at the same temperature. Okay? All right, and so this is our system, and based on how we define this system, during our analysis, we're going to be subject to a couple of different constraints. So the total volume of the system, V, that's going to be the sum of the volume of the alpha phase and the volume of the beta phase. And if we rearrange it, you just get that the volume of the beta phase is equal to the total volume minus V alpha. Similarly, if we look at the total number of molecules in the system, it's going to be the sum of N alpha and N beta. And N beta will just be N alpha, or N, total N minus N alpha. All right. And so those are our constraints for volume and N. But we also have another constraint when it comes to the energy of the system. Because we're dealing with a constant NVT system, the energy that we want to look at is the Helmholtz energy, A. Because if Helmholtz energy is minimized, that tells us that the system is at equilibrium. Okay, so we're going to be looking at A. In any case, the Helmholtz energy of the system is also just going to be the Helmholtz energy, sum of the Helmholtz energy of A alpha plus A beta. Okay? And I want to point out here that this Helmholtz energy for each of the different phases, they're going to be functions of volume and N. So function of N alpha and V alpha, function of N beta and V beta. Okay? As I mentioned, with a constant NVT system, we know that the system reaches equilibrium when the total Helmholtz energy is minimized. So to find the equilibrium state, the stable state of our system, what we need to do is we need to minimize the total Helmholtz energy with respect to N alpha and also V alpha. Okay? And we're picking just only the N and the V of the alpha phase because remember, we have these constraints up here. V beta, or V, that's going to be constant in our system because we have a constant N and V T system. So V is constant. And so really, and V beta, we rewrote it so that it's just a function of V alpha. Same thing over here with the N's. All right, and so here, by doing that, we help reduce the number of independent variables in our system. Okay, in any case, we want to, in order to find the equilibrium state of the system, we need to minimize A with respect to N alpha and V alpha. And so what we're going to require, and so as you remember from Calculus 1, whenever you talk about minimums of a function, what you're actually talking about is the case where the derivative of the function with respect to some variable is equal to 0, right? Okay, and so here, what we want to do is to find the minimum of the Helmholtz energy with respect to N alpha and V alpha, we're going to take its partial derivative with respect to those variables. And so we take the partial derivative of A with respect to N alpha at constant V alpha, and then also constant N, total V, and T. We'll do the same thing with V alpha. Okay? So these derivatives are going to be equal to 0. Okay? And so, if we say that let's start with looking at the derivative of A with respect to V alpha. Okay? And so we say that this partial derivative needs to be minimized. Okay? So this is the partial derivative of total A. And we know that total A is equal to the sum of the A's of each of the phases. And so if we're differentiating total A, what we're really differentiating are these. Okay? So we need to write out their partial derivatives too. And for now, just for brevity, I'm going to stop writing this NVT, but they're still actually going to be there, right? So still remember that this is a constant NVT system. Right? In any case, there should be a V. V and constant N alpha. And so this is A alpha. And then we're going to take the partial derivative of A beta with respect to V alpha, constant N alpha as well. Okay? Now for the Helmholtz of the beta phase, I'm differentiating it with respect to V alpha, but it makes a little bit more sense to, think about A beta, not in terms of V alpha, but more in terms of V beta. All right? So being able to study it as a function of that. Okay? And so what we're going to do is we could rewrite this partial derivative here in terms of V beta by doing this. V alpha. By kind of like doing a mini expansion rule. So now on the bottom we'll have V beta at constant N alpha and multiply it by dV beta dV alpha. That's hard to read. Let's see if I could get a little bit more room by moving this over. dV beta over dV alpha, constant N alpha. Okay? All right, so we expanded the partial derivative like that. But if we remember, based on our constraints here, volume is conserved. And so, if we have any increases in V beta, that's going to lead to decreases in V alpha, and vice versa. All right, and so what that means is that this partial derivative here, they're antagonistic towards one another. And so this partial derivative we have is actually just equal to -1, right? And that comes from the volume balance here. Okay? In any case, so that's -1. So we have this term minus this term. And we're looking at the minimum of the total Helmholtz energy here. So that's still equal to 0. And so what we could do is we could rewrite dA alpha over dV alpha at constant n alpha is equal to dA beta over dV beta constant n alpha. Okay? And I'll also emphasize this is constant t. Alright, so we have this result, but what does it mean? What is this result useful? Well, what you have to remember is we have these partial derivatives here. And if we have these partial derivatives, what we need to do, this is a key that we need to start thinking about the calculus of thermodynamics and start thinking about, what the fundamental equations of our different energies are. And so if we think back to chapter 6, and you recall that the total derivative of the Helmholtz energy was equal to S dt minus P dV, right? The canonical variables for the Helmholtz energy were temperature and volume. And specifically, if you took the partial derivative of Helmholtz with respect to volume at constant T, what you would get is negative pressure, right? Based on this equation. And so what we have on the previous page is dA alpha dV alpha is equal to dA beta over dV beta. And so these partial derivatives we have here are actually describing the negative pressures of the system. Okay? And so our equality from the previous slide, using our calculus of thermodynamics, actually tells us that when we minimize the Helmholtz energy with respect to volume alpha, what we find is that at that situation, at that instance, the pressure of the alpha phase is going to be equal to the pressure of the beta phase. Okay? So mathematically, that's what we showed, and so I'm just going to write it in words. And so what we have is that at equilibrium, the pressures of the two phases are equal. Okay? Alright, and so that's what we get. That's one of the criterion for the equilibrium of our system in which we have two phases going on. In order for those two phases to exist and to be stable, the pressures of those two phases need to be equal.